Good morning, good afternoon, or good evening, depending on wherever you're watching this from or listening this from. This is a weekly science review sponsored by Vetri Labs. Here we take a paper that's published in the open source rather, in the field of electrochemistry and electrochemical engineering, and we do a deep dive. And different professionals lead the sessions. Today's session is going to be led by Dr. Ayyappan Ilangovan, who is a research scientist at Vetri Labs. Over to you, Dr. Ayyappan.
Yeah, thank you, Dr. Chok. Let me share my screen. Yep. Hello, everyone. Today we'll be discussing about direct insights into the role of epoxy groups on cobalt sites for acidic peroxide production. Peroxide is an important chemical commodity as it's been widely used in the environmentally benign oxidant and also potential applications, potential carrier in other applications such as wastewater treatment, disinfection, chemical synthesis, paper or pulp bleaching, semiconductor cleaning, and fuel cells. The global demand of peroxide is growing rapidly, reaching about 4 billion US dollars in 2017, and it is expected to be around 5.5 billion US dollars by 2023. Currently, about 95% of peroxide is produced in the concentrated form using the anthraquinone process. But the drawback of this process, it produces safety concerns when you're transporting the concentrated peroxide, and it also generates organic byproducts. So overall, you have an eco-friendly and an economic process. So another best alternative for this is electrochemical reduction of oxygen via the selective two electron transfer pathway as a as a promising alternative. So the oxygen reduction reaction will enable the decentralized production of peroxide based on the demand under the ambient reaction conditions without any hazardous byproducts. Also, the matter of fact, we need only dilute peroxide is required, indicating that anyway we're gonna dilute the concentrated peroxide before usage. Also, the overall process, if it's integrated with any renewable electricity supplies, you can consider the generated peroxide as a renewable chemical. And in alkaline media, the production of peroxide is somewhat constrained because of the decomposition of the peroxide at a pH value above 11.6, and it requires chelating agents such as EDTA to prevent this peroxide decompositions. So in acid, but it works best in acidic media because the selective production of peroxide via oxygen reduction reaction requires the catalyst materials to absorb on the reaction intermediate with a suitable binding energy that could facilitate its single electron reduction to peroxide, but suppress the further reduction to water. So based on different catalysts that has been used, porphyrins containing 3D transition metals such as iron, nickel, cobalt, with an optimal binding energy towards the OOH, found to be an effective and selective homogeneous catalyst for this peroxide production in acidic media. While these unstable nitrogen ligands under the harsh reaction conditions will inevitably leads to a rapid performance loss. Therefore, it is important to develop an effective method so where you can stabilize this metal nitrogen active species as well as you can maintain their high selectivity towards your peroxide production under like high corrosive environments such as in strong acid. So the best approach is forming the single atom catalyst on a carbon substrate to stabilize this nitrogen coordinated metal centers called this metal NX. And apart from that, when you use a carbon substrate, you'll have a conductive support. So that will enable the maximum exposure of your active metal sites. And based on the other three transition metals that have been commonly used, cobalt-based composites exhibits less deleterious effects, like you have the active sites demetallation or the Fenton reaction ratio. So that would eventually lead to the deactivation of the catalyst in acid. So this current study is focused on cobalt and nitrogen co-doped carbon nanotubes composite, and used it for oxygen reduction reaction, where they're producing peroxide via a two electron transfer pathway. Moreover, they modified the oxygen functionalities around this metal nitrogen sites so that they can significantly enhance the catalytic performance with almost nearly zero over potential and 100% selectivity towards peroxide. And the reported activity is exceeding all the state of art catalyst and benchmarks catalyst reported in the literature. And they did a series of spectroscopic measurements to identify the specific functional groups in promoting this peroxide production, and revealed that the exceptionally enhanced performance for this peroxide generation originates from the presence of this epoxy group that are near the CON4 centers, which resulted in the modification of the electronic structure of these cobalt atoms. Finally, by employing this epoxy functionalized cobalt nitrogen doped carbon nanotubes as the cathode catalyst, a customized peroxide reactor was fabricated that could easily produce about 1200 ppm within 30 minutes, which could satisfy most of the applications such as in water treatment. So how they did the synthesis and surface treated these cobalt nitrogen doped carbon nanotubes. So to prepare this cobalt nitrogen doped carbon nanotubes, they used 3.5 millimolar of cobalt nitrate salt and 35 millimolar of dicyanamide to have the nitrogen doping, and 2 milliliters of ethanol in an agate mortar mixed, and then they continuously grind to form this thick paste. And then they placed it in a crucible board and heated to about 800 degrees Celsius at a 3 degrees Celsius per minute ramping rate for about 3.5 hours under argon to get this final catalyst. And then to have any impurities or any undesirable nanoparticles outside the carbon nanotubes, they use the acid leaching using 0.5 molar sulfuric acid at 90 C for 4 hours. And then for comparison, they also prepared iron nitrogen doped carbon nanotubes and nickel nitrogen doped carbon nanotubes by similar pyrolysis process, by just changing the metal precursor to iron nitrate or nickel nitrate. And then they the effect of carbonization was a time on the peroxide productivity was investigated in detail, and they found out that the pyrolysis temperature needs to be at 800 C. Then that would give the highest overall activity towards peroxide production. So to obtain, they electrochemically modified to generate these epoxy groups. So first they did was peroxide treated cobalt nitrogen dope CNTs, where they dispersed the catalyst powder and heated it in 50 milliliters of 0.1 molar perchloric acid containing 5.8% peroxide under 70 C for 2 hours. And they also did electrochemical activation to again get the epoxy group by oxidizing this cobalt nitrogen doped CNTs through an anodic linear strip voltammetry scan from 1.2 to 2.4 volts, and then subjected it to an electrochemical reduction process via cathodic linear strip voltammetric scan from zero point 0.6 to minus zero point 0.6 versus RHE. And so they combine these two peroxide treatment and electrochemical activation, and they call it as HE cobalt nitrogen doped carbon nanotubes, and basically combining both the process, first doing the peroxide treatment and then using that as a initiator to do the electrochemical activation. And they also did the hot alkaline treatment of this aged cobalt nitrogen doped carbon nanotubes in 6 molar KO solution with an autoclave reactor under 180 C for 12 hours to see how the other functional groups could do. So basically, when they do this alkaline treatment, they get hydroxyl groups, and they compared how that would be compared in the presence of hydroxyl and epoxy groups. So the electrochemical measurements were all performed in 0.1 molar perchloric acid in a 3 electrode system, and they did the oxygen reduction activity was used by RRDE measurements in oxygen saturated electrolyte at a scan rate of 5 millivolt per second. And here they coated their glassy carbon electrode with 5 milligram of the prepared catalyst. So they made a catalyst ink by having the 5 milligram catalyst with 25 microliter of naphthalene solution and 1 ml of ethanol to form a homogeneous ink, and then they drop casted 6.5 microliter of that ink to get a loading of about 0.25 milligram per centimeter square on your working electrode. And they used a graphite rod as their counter and a saturated calomel electrode as their reference electrode. And they used the pH factor, and they converted the electrode potential to reversible hydrogen electrode, and they did not do any correction for the system resistance. And in later slides, they identified the concentration of peroxide, and they also did the electrocatalytic protection of peroxide, were measured in the two compartment cell with Nafion membrane as separator. And they filled both the cathode and anode compartment with 75 milliliters of 0.1 molar perchloric acid, and they were continuously purging oxygen into the cathode compartment. And they were using a hydrophobic carbon fiber paper loaded with the prepared cobalt nitrogen dope CNT catalyst, about 0.5 milligram per centimeter square as working electrode. And the graphite rod was counter, and saturated calomel was their reference electrode. And they calculated the concentration of their peroxide by using potassium permanganate titration. First, let's look at their microstructural analysis. So as we see here on the SEM, they were able to find this carbon nanotubes present, and then with the help of TEM, they could see that there was a bamboo-like feature resembling the CNT backbones, and their diameters range anywhere between 50 to 200 nanometers. And on the inset, you can see the lattice fringes, and there was about 0.35 to 0.36 nanometer, indicating the 002 graphitic plane, because in the densely packed graphitic structure you have it about 0.34 nanometers. So this expansion, like this increase, tells us that this could have been expanded due to the doping of cobalt and nitrogen. And they did the elemental mapping of a selected area to see how the cobalt, oxygen, nitrogen, and carbon is uniformly distributed across the structure, and demonstrating that they were successfully able to dope both cobalt and nitrogen into the catalyst. And they did the high angle annular dark field scanning transmission atom microscope to see the like how the cobalt atoms are dispersed. And as you can see, the bright dots corresponds to this cobalt atom that are homogeneously dispersed throughout their carbon nanotubes. And they performed electron energy loss spectroscopy in a selective area within this figure D to reveal this existence of this isolated cobalt atoms, so that it's not it's a pure metallic cobalt that's present on the CNTs. And the XPS elemental survey spectra also confirms the presence of carbon, nitrogen, oxygen, and cobalt, so that could see how they have done the successfully synthesize this cobalt, nitrogen, co-doped carbon nanotubes. And to further give insights on this material, they did the ZANs and ZAFs of the material. And as you can see here, for the higher white line intensity and the position compared to the cobalt foil, indicates the existence of this positively charged cobalt with an oxidation state in CON, like cobalt, nitrogen, co-doped carbon nanotubes. And further, we can see the slightly lower absorption edge position, that of the cobalt thalassynine, suggests that the valency state of atomic CO is situated between 0 and 2 plus. And as we can see in this region, you can see the absent. There is no presence of this pre-edge future that could arise from the transition of 1s to 3D at that 7709 EV. So that, which indicates that there is a symmetric coordination, that is the CO with 4 nitrogen atoms. And based on the ZAPs, they can see that the ZAP spectra exhibited a signal of about a light scattering radius 1.5 Armstrong, corresponding to this CONC scattering pair, and further giving the existence of this cobalt coordinated with this 4 nitrogen atoms. And the weak signals originated from this CO scattering path in a metallic future can be ascribed to this rare appearance of these cobalt nanoparticles. And further, they evaluated the electrochemical performance. So they did the ORR measurements in an RRD setup where they have a glassy carbon disk where the working like where their catalyst is drop casted, and the platinum ring, which would oxidize the peroxide that is produced during the reduction of oxygen. As we can see here, the cobalt nitrogen codope CNTs exhibit good catalytic activity towards electrolytic production of peroxide and acid, and showing about currents higher than 0.7 volts, and this is about the theoretical potential for peroxide in acidic conditions. And they purchase nitrogen doped graphene to see how that performance looks for peroxide production, and they can see that it doesn't have any peroxide oxidation at all. And as we know, this the majority of the electron since is consumed by this two electron pathway, showing about a very high selectivity. We can see here it's somewhere between 50% to 80%, and in this region of about 0.5 to 0.7 volt, it's somewhere close to 80% overall. And as on this LSV over here, we can see how it compared with the iron and nickel doped carbon nanotubes. And one thing we can notice here is, as expected before, cobalt had a higher peroxide selectivity, and it reduced oxygen through this two electron transfer pathway, because you had about less than 40% for both the iron and nickel doped, and 80%, like twice selectivity for this cobalt dope. And moreover, the Tafel slopes is also lower for the cobalt dope compared to the iron and nickel doped, indicating that the cobalt dope has a faster ORR kinetics, and it further suggests the superior role of this CON4 species in reducing your oxygen through this two electron transfer pathway. So then, however, they start to get into a trouble. So saying like, okay, what would be happening? So they expose this cobalt nitrogen codope carbon nanotubes in air for about 30 days, and they called it as aged CON CNTs. And what they noticed is when they tested the electrocatalytic activity of that, they found out that like the the peroxide production falls drastically. And this indicates that there is occurrence of some unwanted oxidation process on the catalyst because it was exposed to the air, and that could lower the peroxide productivity. So to get their hypothesis validated, they stored the sample in vacuum for 30 days and tested, and they could see that activity could match what they got for the cobalt before aging. So they know that is definitely due to oxidation process that's happening on the surface when it was exposed only to the air. So they to further before going into modifying it, so they try to do some instrumentation techniques to verify what is happening. So they did the uh, XPS to see how the oxygen concentration varied, and what they could see is the oxygen concentration increased from 3.5 atomic percent to 5.17 atomic percent when it was exposed for 30 days. And then they did the high resolution and so then they could split this like what are the different oxygen groups, and then it could be ketonic or oxygen atoms in epoxy, or epoxy oxygen in the ester groups, or oxygen atoms in this carboxyl groups. So after dividing into these and then measuring what is the percentage of each oxygen, they could identify that only the ketonic groups have gone through this noticeable increment, which increased from 0.84 atomic percent to 2.64 atomic percent in age sample. It's roughly about 3 times increase in their ketonic oxygen. So this suggests that their presence of more ketonic groups is responsible for this decreased peroxide productivity on their aged samples. So to get back the peroxide production activity of this aged cobalt nitrogen doped CNTs, they did some electrochemical treatment, and they also did peroxide treatment, and they did a combined treatment to see how they all affected, like how they all improved the activity of this aged catalyst. So for that, first let's focus on the electrochemical treatments. So here, and so they used in the electrochemical treatment, if they use just electrochemical reduction, it will be very hard to remove this oxygen functional groups, which is the ketonic oxygen, because they're thermodynamically more stable than the carboxyl groups. So the electrochemical oxidation treatment is effective in rebuilding the surface oxygen functional groups on the carbon-based materials. So they combine these two. So first they electrochemically oxidize it, and then they use that sample and electrochemically reduce it to electrochemically activate this aged cobalt nitrogen co-doped CNTs. So first they did the electrochemical oxidation treatment, and then as we can see here, the cobalt nitrogen doped composites has a higher oxygen content, 12.66 atomic percent compared to the 5 atomic percent, because of that we apply a high positive potential. And then in specific, apart from the O1, the ketonic group, the O2 on the epoxy and the hydroxy, like epoxy and the carbonyl oxygen, exhibited a higher ratio. However, the ketonic oxygen decreased, indicating that the electrochemical generation of epoxy and carbonyl groups on the cobalt nitrogen doped CNTs, and you would be possibly converting the uh, ketonic group into other oxygen species during this treatment, since we are further oxidizing it. And then they subjected the electrochemically oxidized and CO cobalt nitrogen doped carbon nanotubes, and then they reduced it, and that to afford this electrochemically activated CO and CNTs. And we can see that after this electrochemical reduction process, the O3 and O4 oxygen significantly reduced from 33.2 and 24.7% to 15.9 and 6.9%, while that of this O2, which is from the epoxy, became dominant when they compared with the EVO or else their aged CO and CNTs. So the significantly reduced amount of this O3 and O4 could be correlated to the reduction of some oxygen functional groups like ester and carboxyl under the cathodic potential that we are applying, which coincides with their observations in their previous work. And also the epoxy groups are thermodynamically more stable than their ester or carboxyl groups, and they are hard to be removed by the electrochemical reduction. Therefore, compared with the aged cobalt nitrogen co-doped CNTs, the exclusively increased oxygen species in this electrochemical activated CY and CNTs can be attributed to this presence of epoxy groups on the catalyst. So to further see how the nitrogen doping and the cobalt valency, like the atomic valency state is changing, they did the further analysis to see how the oxygen functionalities impact the rest. So on their nitrogen N1X spectrum, they can see that the peridonic nitrogen, the one at the 400 eV with the 5-member ring, it increased while the pyridinic nitrogen decreased when you electrochemically activate it. So doing this electrochemical treatment, the epoxy groups will be produced will preferably bond to these carbon atoms that are adjacent to this pyridinic nitrogen, and consequently transform this pyridinic into peridonic. So that's why you see decrease in one and then the increase in the other. So then they also did when the cobalt nitrogen peak on the cobalt 2p 3x2 spectra. So what they can see is the cobalt nitrogen peak shifted positively to a higher binding energy on the electrochemically activated catalyst, demonstrating that the electro generated oxygen groups is imposing an electron withdrawing effect that affected the electronic structure of this cobalt atoms. But however, in contrast, the electrochemical treatment did not show any obvious influence on the valency state of cobalt, As we can see here, it still almost remains the same, and it was not +2 or +3 based on their standards here. Then again, on the earlier slide, we saw about the presence of epoxy, and the FTAR results also confirm the appearance of this epoxy functionality, showing the strong absorption band and this 1000 to 1200 wave number. So and then now they verified that there is an increase in the epoxy group when they electrochemical treated it, and then they moved to do a electrochemical study on that. So as they did that, when you can see for the aged, when the aged CO and CNTs were subjected to the electrochemical activation, we can see that we were able to bring back the peroxide production. And now it's even at a higher selectivity. As we can see here, the selectivity was about 80%, and now they can improve the selectivity is about 90%, whereas for the aged one was initially about 20%. And the over potential was almost zero. It starts about 0.7 volts. And then I mentioned earlier that they did this electrochemical production by using this two compartment cell, and on that, so they measured the long-term stability using a chronoamperometric measurement at 0.45 volts for 12 hours, yielding about a current of 10 milliamperes. And then they measured the concentration of this accumulated peroxide using this permanganate titration method. And also one other thing to note here is this current density is about 3 milliampere per centimeter square, which is very close to the theoretical mass transport limit of this 2-electron reduction of oxygen. So then they did this overall activity of the peroxide treated. So that was the other treatment to introduce these epoxy groups. So basically they had so as we saw earlier, they chemically treated it in a 0.1 molar perchloric acid solution containing 5.8% of peroxide. And as we can see, when they compared the aged one with the peroxide treated one, the selectivity, the ring current increases, and so does the selectivity. So the selectivity increased from 20% to about 80%. And so they thought, okay, they wanted to even further enhance the electrochemical production of peroxide and increase its selectivity. So they combined this electrochemical activation and then the peroxide treatment and call it as HECON CNTs. And as we can see here, um, yes, and when they introduced it in air, so of course there is no oxygen reduction, like because of the less amount of oxygen present in air. And then when they completely have just air, and you can see it's about close to 3 milliampere per centimeter square, and then the ring current is higher than what they've achieved for all the catalysts before. And also the onset potential is close to 0.7 volts, suggesting that there is no over potential. And this could, and when they measure the selectivity, they can see it could maintain nearly about 100% selectivity in a wide potential range, and about 0.3 to 0.6, it's about 95% it can maintain that, exceeding the catalytic performance of the state of art or the other benchmark catalyst that is reported in literature for this MNC based. So further, they did this electrochemical production of peroxide by assembling a gas diffusion electrode reactor with purging, oxygen purging on 0.1 molar perchloric acid. Again, they used this carbon fiber paper that had about an active area of 9 centimeters square, which was loaded with the combined treatment, cobalt, nitrogen, codope, CNT catalyst, with a loading of about 0.24 milligram per centimeter square as working electrode. And they used platinum carbon loaded onto this carbon fiber paper as the counter electrode. And here we can see the performance of the reactor, and the inset shows you the chronoamperometric curve that was obtained at 0 volt RHE for peroxide production, giving it about 9 milliampere per centimeter square. And further, they calculated the concentration of the peroxide that is accumulated over 12 hours time span at not at 0 volts, and this was done at more moderate potential of about zero point 0.3 volts. And initially, they had a current density of about 4 milliampere per centimeter square. And then the concentration of peroxide in the first 30 minutes was about 374 ppm, and it further increased to 3179 ppm after 6 hours, and it's finally reached to about 5500 ppm after 12 hours of peroxide production. So in summary, so they demonstrated that by modulating these oxygen functional groups near the atomically dispersed cobalt sites with proper electrochemical and chemical treatments, you can obtain a highly active and selective oxygen reduction process for this peroxide production in acidic electrolyte, and showing a negligible amount of onset over potential and nearly 100% selectivity in full potential range. And they combine spectroscopy results to reveal this exceptionally enhanced performance of the peroxide generation is indeed originating from this presence of epoxy groups near the CON4 centers, which resulted in the modification of the electronic structure of the cobalt atom. Then the electronic structure has been tuned. So as a result, it's tuned by the presence of epoxy groups, resulting in close to ideal binding energy that allows the ORR to proceed via this 2-electron transfer pathway to produce peroxide and not directly reducing it to water, where they observed this in the case of iron or nickel. So both the electrochemical activated and the combined composites exhibited record-breaking peroxide productivity, outperforming all the catalyst materials reported previously for peroxide. And the authors says that further optimization of this catalyst materials as well as devices obtained in the study, including improving the long-term durability to several thousand hours, or faster mass transport in the electrolyzer, and accelerated production rate, high peroxide production rate in air will be carried out to warrant their future practical applications. So with that, I would like to thank you all, and we can move on to the discussion.
Great. Thank you, Ayyappan. That was a very nice summary. Now is the time for discussion. Gitanjali, any thoughts, comments, questions?
Yes, a nice. Yeah, Dr. Yapa nicely presented you this paper. Yeah, I have one question. They have selected only cobalt. Why? Why? What about other transition metals? Is there any
They
specific
did test
property
it
for
with
the cobalt?
they were attributing that the cobalt can form this CON4 active sites compared to the iron and nickel. But I've seen the iron FeN4 active site, like when they form that metal active site, it actually does the ORR through a 4-electron transfer pathway. So that's probably
Okay.
why we saw less selectivity towards peroxide. And so they did the initial analysis with all these three, and they saw that okay, cobalt was the one that has the higher selectivity, and then they did the further analysis based on that.
Okay. Thank you.
Yeah, related to this, I don't know what is the distance. They talked about the zero point 0.3 to zero point 0.4 nanometer gap, right? Compared to the
Yes.
angstrom gap that's needed for the 4 electrons. Otherwise, it will combine
Yes.
and form the water.
Yes.
So I wonder if
What?
that spacing is impacted by the iron and nickel. I don't know if they commented on the spacing. They commented on the spacing of
No,
cobalt.
they didn't. Yes,
Yeah.
they haven't on the iron or nickel. So that
Okay.
could be the reason, because it could directly form the water.
Right. It may be closer. I don't know what the sizes and the things are with that
Yes.
coordination. Yeah. Go ahead,
Yes.
Gitanjali.
They did a lot of, yeah.
Yeah,
No.
sure, Dr.
They did
Yapa.
a
Go
lot of
ahead.
theoretical. Yeah, they did a lot of theoretical studies. I haven't included that on the paper, but that was more detailed to analyze and understand that. So maybe there they might have had some more insights into why they prefer cobalt on the later part of their paper.
Yeah. Yeah. Other comments, questions, Gitanjali?
So this is only this is only
Okay.
that was
Got
only
it.
one question because
Yeah. So, yeah,
I'm not
understood.
aware with this field too much.
Yeah. No
Totally
problem.
catalyst field is this.
Correct, correct.
Yeah,
Yeah, what I liked is I truly saw this as engineering at the atomistic and molecular level.
exactly.
Yeah, they were looking at specifics, and went into the fundamentals, really understanding, doing the XPS analysis, and doing really resolving the peaks, oxygen peaks, and a very nice and detailed fundamental study. One question I had is when they had the 0 volt versus RHE, I would have expected some hydrogen evolution happening. Wouldn't that
Mhm.
impact the peroxide generation? Did they comment anything on that?
I I think it would no. All these information were in their supplementary. So
Okay.
on that added note, they had about 55 pages of supplementary information with about 40
Wow.
figures, whereas on the main manuscript they had only 4 figures
Okay.
and 40 figures. So I was trying to take it from their supplementary information to see this is what they've done, and they didn't comment much on that information. Yeah.
Okay. Okay. Yeah, it's very
They were
well
focusing
done.
on
Yeah, very well done paper. Lots of details for sure. Yeah.
yes, yes.
Mm.
They were focusing only on the concentration, like how much peroxide they can produce at what time, and they were
Mhm.
attributing okay for this industry this concentration is enough and things like that.
So even if the Faraday efficiency is not all that great because of hydrogen evolution, they're okay as long as you have the right peroxide concentration.
Yes, yes.
Okay.
And I think you are right. There could be hydrogen production because I remember reading it that the Faraday efficiency dropped about 65% from 87% or something.
When they went to the 0 volt versus RHE.
0 volts.
Okay.
So I
Okay.
think that could be the.
The
But yeah,
reason.
if this paper is yeah, this paper is I think everyone should read this paper detailedly. So whenever you have a question, you go to the supplementary. They have done an analysis. They have
Yeah.
done so they have like tons of analysis. I don't know how long they spent in doing this, but it was very well written.
Yeah. Yeah. Great. 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 Thank you very much, Ayappan. Again, it was a very nice presentation and summary. And we do this every week. So if you'd like to lead any of the papers, please do reach us at info@vetrilabs.com. We'll be meeting every Thursday as of now, but that may change in the future based on what the feedback we receive from participants.
Mm.
Thank you again.
Okay, thank you, sir.
Thank you.